Hello and good day, geometry. We're opening up Unit 7, which talks about quadrilaterals. But we're going to start with just another feature of a polygon, which is called a diagonal. Does anyone know what a diagonal is in the geometric sense? We know what a diagonal line is, right? And it's one that looks like that, perhaps. But in the geometric sense, what does a diagonal do? Any idea? Yes.
Straight line across a figure.
Okay, essentially yes. A diagonal connects two non-adjacent vertices of a figure. Okay? A diagonal connects two non-adjacent vertices of a figure. So it's possible for a figure to have more than one diagonal because if I start at this vertex here, which is just kind of like a corner, I can draw a diagonal across to that vertex there, and I can draw a diagonal down to that vertex there. Right? So that term diagonal can be kind of misleading because especially this diagonal going across here, it's almost a horizontal line. It's not really diagonal, right? But it does what it's supposed to do, which is connecting two non-adjacent vertices. I can also make some diagonals from this vertex here. I can go up like that and up to that vertex, there. I can also make one going up like that. It is a star. Isn't that cute? Bet you didn't see that one coming. Okay. So how many diagonals total does this figure have here? 5. Okay. Well, so Sebastian said, is it 5 because it's a 5-sided shape? Well, Daniel said, is it 5 because it's a 5-sided shape? Well, let's kind of test that. Here we've got, looks like an 8-sided shape, an octagon, and let's draw all the diagonals here. And like anything else, okay, it's very helpful to go at it with some sort of order, some sort of process. Don't just draw, I see this diagonal and this one and this one. Pick a vertex to start with, folks. Pick a point to start with and draw every diagonal that you can from that point. We're already at 5. I don't know if our 8 diagonals for an 8-sided shape will hold here. But that's all the diagonals we can draw from that particular point. I'm going to do my next point in red, just kind of keep these somewhat organized. Okay. Diagonals can be drawn down here, 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 and here. Yes, spoiler alert, we're going to get a lot more than 8. Okay. Well, that's why doing it in separate colors might help here. I've already done 5 of them in green. I've done 5 of them so far in red. Keeping a tally as you might be easier than count them all up when you're all finished. Going over the next point, which we'll start drawing these in blue here. 1 going down there. 2, 3, 4. Why can't I draw a 5th diagonal with the blue?
There's already one there.
Because we already drew the one connecting these 2 points in green. Okay? So there are only 4 that we drew in blue. Side conversations, folks. Take them down. Thank you. For our next point here, I can draw 1 over here, across, 3, and that's all I can do because I've already drawn 1 diagonal in green here, this one going down like that, and 1 in red here, that one going down like that. So 3 in black. Okay? We start to see a pattern here. How many diagonals, I'll go back to green again. How many diagonals can I draw from my next point? Right here. I can draw two new ones, right? I've got a blue one going up here, a red one going straight up, a green one going diagonally across there. I can draw 1, 2. And then we'll go back to red, I suppose, from this one here. How many diagonals can I draw? Just one. Okay? And that's all of them. So total, it looks like we got what? 5, 5, 14, 17. We've got 20 diagonals drawn there. Okay? So when you see the word diagonal, it's referring to a segment that connects two non-adjacent vertices inside of a polygon. And the reason why we are covering this now is because diagonals actually play a big role in quadrilaterals. And so that's where we're headed, just an introduction to it here. Okay? Questions on this? Because we're going to shift gears a little bit. All right, next up, we have two theorems. The polygon interior angles theorem and the polygon exterior angles theorem. What is the sum of the interior angles of a triangle? You should know this off the top of your head after 5 months of dealing nothing but Alan. 180. How about a four-sided figure? Anybody know what the sum of the interior angles is of a four-sided figure? 360, right? Square rectangles have four right angles, 360. What about a pentagon, a five-sided shape? Anybody know what the sum of the interior angles is there? Yeah. 540.
It's going up by 180.
What about a hexagon? The sum of the interior angles of a hexagon. Evan, 720. I heard someone say the pattern. What's the pattern here?
It just goes up by 180.
Goes up by 180. So is there some sort of formula that will allow us to relate the number of sides a figure has to the sum of its interior angles?
Yes.
There is. Good. Now what is it? Noah? Well, not necessarily. Like for a triangle, 3 angles times 180 is going to be larger than 180. Sebastian?
Do the total angle degree divided by the total number of sides.
Angle degree divided by number of sides. So 180 divided by 3 is 60. That would tell us what each angle is. This is an equilateral triangle. But I'm like, if I ask you for how many, what's the sum of the interior angles of a 14-gon, a 14-sided shape? Is there some sort of formula, which you already answered yes, and there is, that will allow us to relate the number of sides of a polygon to the sum of its interior angles? Nick?
90 times whatever amount of angles?
Well, 90 times 3 is 270.
Wait, no.
Brent?
60 times the number of sides?
60 times 3 is 180. 60 times 4 is 240. Mackenzie?
The number of sides minus 2 times 180.
Got it. Good. The formula is 180 times the number of sides minus 2. Okay? Since we're starting with a 3-sided shape at 180, and we're increasing from 180 each time, 3 is kind of our beginning number, right? So 3 minus 2 is 1 times 180 will give us 180 degrees for a triangle. A pentagon, 5 minus 2 is 3. 3 times 180 is 540. So a 14-gon, the calculation that you would need to make is 180 times 14 minus 2, or 180 times 12, which is, what is it? 2,160. Okay? So that formula enables you to calculate the sum of the interior angles of any polygon by subtracting 2 from the number of sides and multiplying by 180. Okay? The polygon exterior angles theorem is a lot simpler. Every polygon's exterior angles add to 360 degrees. Every polygon's exterior angles add to 360 degrees. Regardless of whether it's a triangle, square, pentagon, hexagon, octagon, 14gon, or whatever. Okay. Now, what we mean by exterior angles, here's an example here. Okay. The exterior angles of a polygon can be formed by kind of extending each side, right? Each side here has kind of been extended, and the four angles that are created from that would be the exterior angles of that polygon. So what formula, or what equation rather, would you set up to solve for x there in that given example? Noah?
3x plus 89 plus 67 equals 360.
3x plus 89 plus 67 equals 360. It'll equal 360 every single time. Okay, that's what the theorem states, that it has to. And where the 3x comes from, we've got 2x, we've got 1x, combined like terms, total that's 3x. And our other two angles, 89 plus 67. So combine some like terms. 89 plus 67 is 156. So 3x plus 156 equals 360. Subtract 156 from both sides. We get 3x equals 204. And divide by 3, x equals 68. Okay, Noah. Yeah. Quickly, I'll pause the video so you can do this with your table mate or by yourself. Answer these three questions here involving interior and exterior angles. Actually, these are all interior angles here. So I will pause. We'll come back, talk about it shortly, but do that now, please. All right, so we are going to go over the answers for these three. The sum of the interior angles of an octagon having 8 sides, that means you are essentially going to be taking 180 times 6. Subtract 2 from the 8. 180 times 6 is 1,080. And that would be the sum of the interior angles for an octagon. No matter whether it's a regular octagon like a stop sign or if it's a funky, messed up octagon, if it has 8 sides, its interior angles will add to be 1,080. For a 13gon, you're essentially taking 180 times 11, which is 1,980. The sum of the interior angles of a 13gon. And then this one kind of switches it around. This says the sum of the interior angles of a polygon is 900, classified by its number of sides. How did you answer this one, Sebastian?
So I did 900 divided by 180, which equals 5. So 5 is like the answer you have to add to it. I can do the reverse in the order.
Okay, so we can use this formula, only we're solving for n. Rather than being given n, we're being given the sum of the angles. That's what this formula equals. So dividing by 180, n minus 2 has to equal 5. So it has to be a 7-sided shape, which is a heptagon. Nick.
Well, I was going to say something that won't always happen, but I was saying that I looked at the first question, and I saw that that 8 sides, like an octagon, is 1,080. So, and then I was like, if it's above or below. So I looked at the numbers below. So I started at 7.
Oh, I got you. You're okay. Okay, yeah. Nick is using some prior knowledge to help here. He's saying that we already figured out that an 8-sided shape, an octagon, is 1,080. So 900, which is 180 degrees less than 1080 would mean it has one less side. So that's where you get the 7 sides versus the 8. Very, very good. Yeah. If you got prior knowledge to use, then by all means. Gabby.
Do we need to know like the exact classifications of the shapes like a heptagon?
Yes. If I ask you for a 9-sided shape, you should be able to tell me it is a nonagon and all that sort of stuff. Yeah. Up through 12. Yep. A dodecagon is a 12-sided shape. Dodecagon. It's just an 11-gon. Yeah, it's just an 11-gon. Okay, next one. I think that was it for that. Good. We're going to end this video for CO44 and then make a new one for CO45. So just sit tight. You can, while I pause and end the recording, you can do your wrist exercises because you can see that 45 is all note taking. So here we go.